So next up on the periodic table, we have the group that's known as the halogens. They're also known as group 17, so they're way on the far right side of the periodic table. So this includes fluorine, chlorine, bromine, iodine, and astatine. Okay, so with these, they have 7 electrons in their outer orbital. All of these well, for the most part, all of these elements are trying to get to 8 in their outer orbital. So these elements like to react. They generally tend to react violently, highly reactive, especially fluorine, because they are so close to getting that outer orbital complete. Okay, they're so close to getting 8 in the outer orbital. They readily form what's known as -1 ions. Okay. And then the reactivity actually increases as you go up. So again, fluorine is the most reactive out of all of these. And finally we have, well not finally, but next up we have group 18, which is the far right column on your periodic table. It is the noble gases. So we talked about these briefly in the last chapter. They already have 8 electrons in their outer orbital. So they don't really want to add any more, and they don't want to lose any. They're happy the way they are. So they are mostly non-reactive. Some of the larger ones, like krypton and xenon, will react under certain circumstances simply because they're so large that they basically forget they have 8 electrons in their outer orbital. So they do not generally form ions except for krypton and xenon. Okay. And then next up, we have the lanthanides. So the lanthanides are actually named after the first element in the series. So it's lanthanum, okay, this element 57 here. So the lanthanides are actually, they will fit into the periodic table right after barium. Okay, so they actually will fit right in here. Okay, right there. Alright, so sometimes you will actually see where lithium is at the end here next to ytterbium. Okay, and then they will leave this square basically blank, and it'll say 57 to 71. Okay. Other times, like this one here, they just have these elements on the bottom, and then just assume that you know that they fit in here. Okay. Other times they will actually have an arrow that draws down from there, various different ways. Okay, only promethium, right here, PM, is radioactive in its most common form. Some of them are synthetic, some of them are not. They were relatively difficult to discover simply because of how large they are. They're not very common elements for the most part. Yeah, and I wouldn't be surprised if you don't recognize any of the names in this series, in the lanthanides. Okay, so next up we have the actinides. So these are probably going to be slightly more familiar. They are incredibly similar, at least in setup, to the way, to how the lanthanides are set up. So the actinides fit into the table right after radium. Okay, so element 88. So right there. And most of them are synthetic. There are a couple that are natural. All of them are radioactive in their most common form. Thorium and uranium, so TH here, thorium, and then uranium, U, do actually have a stable form that's not radioactive. They are not the most common forms of each of these elements, but they do exist. So again, some of these you might recognize the names a little bit more. Like thorium, uranium, neptunium, plutonium, okay? Then you've got americium, curium, berkelium, which is actually named after a university, Berkeley, californium, einsteinium, mendelevium, okay? He actually created this periodic table, and then nobelium as well. Alright, so finally, you won't always see unknown elements on the periodic table. In fact, the most recent version of the periodic table doesn't have any unknown elements. These are either recently discovered or synthesized, so created, or they're currently theoretical. Okay, so there's kind of a wide range here. Again, like I said, with their names, they are based on the Latin name for that number, or the Latin word for that number. They are generally created using what's known as a particle accelerator. So particle accelerators, they do basically exactly what the name says. They accelerate particles. So you will take usually very specific atoms, sometimes they're large, sometimes they're small, and you put them in a particle accelerator, which is basically just a giant tunnel, giant circular tunnel. And it's designed to get these particles spinning in these giant circles really, really fast. And once they've reached a certain speed, the scientists will actually maneuver them so that they crash into each other. Okay? And then they take a readout of what happened at the moment of impact, and they can tell if they created a new element or not. They can tell a bunch of different things from it. The most famous particle accelerator is known as the Large Hadron Collider. Okay? So, the Large Hadron Collider is this little one here. So it's halfway in France and halfway in Switzerland. Okay, they are looking at building a larger one. It's the Future Circular Collider, FCC, okay, which would be much larger. The LHC, the Large Hadron Collider, is about 27 kilometers in circumference. So it's huge, but it's not necessarily big enough to continue with some of the work that they want to do. Hence why they're building the FCC. Okay. Well, that thought just ran away. Oh, right. Okay. So, I do have some videos that talk about kind of why they're looking into basically smashing these atoms together to create larger and larger atoms. There is a theory that there is something called a super heavy element, which would be like basically a massive atom that is stable. So it's not radioactive. It stays around for more than like a nanosecond, which is about how long each of these new elements exist for. But they actually are predicting that a super heavy element, if it were stable, could actually, have a bunch of different properties that we've never really seen before. And I'll show you something in a second that kind of took that idea and ran with it. But again, Large Hadron Collider particle accelerators are just giant tunnels. Okay, so this is what it looks like from the outside, and then that is what it looks like on the inside. Okay, and then this is the type of readout that they get from this kind of collision. So you can see here, right in the center, this is where the two particles would have collided. And then you can see all of the energy and different pieces of those particles that kind of get shattered out from that impact. And that's about as much as I know about this. This is high-level quantum physics, which I don't necessarily deal with. So I can tell what this is, but I can't tell any information from it. And don't worry, that is really high-level math, and we're not going to go into it. But particle accelerators tend to end up in pop culture. May not necessarily realize that. There have been two recently with comic books that have actually, well, not necessarily recently, but two comic book uses of them. So you might, if you're a Marvel fan, if you remember back in Iron Man 2, when Iron Man is getting poisoned by his little arc reactor that he has, I think he says it's the palladium poisoning, which is a real thing, but he ends up creating a new element. So he actually creates a small particle accelerator in his basement in order to help him create this new element. Yeah, you can see a couple differences between Iron Man's particle accelerator and the Large Hadron Collider. Mostly the Large Hadron Collider is so large that you can't actually tell that it's curved, okay? And Iron Man's is tiny, okay? You also wouldn't necessarily want to create a beam like this coming out of it, so it's incredibly dangerous, but, you know, he's Iron Man, so I guess it works. The second one, if you watched, or if you watch The Flash, okay, the TV series The Flash, it was actually a particle accelerator explosion that caused the lightning strike that turned Barry Allen into the Flash. Okay, so this is showing kind of like the immediate aftermath. Not really feasible. I'll go ahead and just say that. But it was, you know, a use of a particle accelerator that you might have seen. Okay. Another problem that I have with both of these is that their particle accelerators are actually above ground. Yeah, you wouldn't necessarily want to do that for like cooling reasons, stability reasons, because if there's like a tremor from, say, a highway nearby, you can actually throw off the entire experiment. So again, don't necessarily want to be above ground with these particle accelerators. But alright, so going back to the periodic table, another look at it. This periodic table shows you a couple different things here. So it does have the breakdown of the different group names, okay? And then it also tells you about, you know, what type of element it is, okay? And then if you'll notice here, it does also have something about the state of the matter, so whether it's solid, liquid, or gas. So you'll notice that the majority of the elements, especially all of the metals, or most of the metals, are solids, okay, solids at room temperature, and this is in its most common form, okay. But then you'll also notice that you have some like hydrogen, nitrogen, oxygen, and obviously all of the noble gases over here. They are gases at room temperature. And then you've got just two elements that are liquid at room temperature. So you've got bromine and you have mercury. Okay, so that's pretty unique there. And then the ones that are just the outline are your synthetic elements. Okay, so again, you can see all of that. This periodic table is slightly more updated because it does have two of these elements named. Okay, so flerovium and livermorium, they do have names for all of these elements now. Okay, like moscovium, oganesson, and tennessine. I forget what the other one is, but yeah. Okay, so just wanted to draw your attention to that. Also want to draw your attention to these charges that I've got at the top of each of these groups, not periods, but groups. Okay, this is basically a breakdown of the charges that we were talking about earlier. Okay, so everything in this column likes to form +1 charges. Everything in this column, the second one here, likes to form +2. And then third column over here, skipping over the transition elements, the transition metals. Okay, so this column here likes to form +3. The column that starts with carbon is either a plus or -4, and then you've got -3, -2, and -1. Okay, so that's kind of the easier way to remember what the charges on each of those elements are. Okay, and again, we'll get more into that later, so I'll bring that up again later. But alright, so that is the end of chapter 1. So, actually, I lied. I wanted to show you this one more thing. So some of the element names, you might notice that their chemical symbol looks a little bit off based on the name itself. Those are mostly from Latin. Okay, so like iron in Latin is ferrum. So we still talk about like ferrous things, and it's Fe. Gold is aurum, so Au, tungsten, wolfram, And then, yeah, you can look